All right, here we are again. So now I just want to go over to Moodle for a second. I think I have already. No, here it is. No, that's not it. Okay. All right, let me go open it up again. All right, so there's one thing I need to post on here, which I forgot to do. So I'll do that right now. And that would be the second sample midterm. Hold on one second.
This is the second midterm.
It's coming up really soon.
When?
Hold on one second. Let me post this. And so here we go. I'm going to put this up there, right? This is the second sample midterm. Now, this is midterm number 2, sample midterm number 2. Now, I think I mentioned once before that the second midterm is entirely based on Chapter 8. And so we finished Chapter 8 a while back, and we also finished the Chapter 8 problem set. And in fact, here are the problems set solutions right here if you want to look at them again. And so you can see all the details are there. All the numbers are typed in along with the explanations. And what else is here? Well, all the answers are here, including all the formulas. Everything you need to know about Chapter 8 is contained in this document. So, but just for the practice, we're also going to have our second sample midterm. So I would like you to get this ready for Monday. And you can see it's really the same stuff. And then I can post on Monday when we're done with this, I can post the actual midterm. And then, you know, you can have about a week to do it, I guess. That would give you a full weekend. It's not going to be as long as the last one. Let's put it that way. And again, because it's based on just one chapter instead of 2. So it'll be a lot quicker than the first one. The final won't happen for quite a while. Officially, if you look at the May calendar, I had it here somewhere. Here we go. According to the.
Sorry to interrupt. When is the midterm when is the midterm? Do you know?
Well, I'll post it as soon as we're done with the sample midterm next Monday.
Okay. My next question is, wait, I had another question. Is it another take-home midterm, or is it?
Oh, absolutely. It's exactly the same format.
Okay.
You'll download it and do it at home.
Okay. Thank you.
Yeah, absolutely. So yeah, officially the finals week is supposed to run from the 13th to the 19th, which is quite a ways down the road. Now, the final exam is just based on chapters 11 and 12 only. It is not comprehensive. So depending on how long it takes to finish chapters 11 and 12, we may actually finish a little early. Also, I think that the school is closed on the 10th. So somewhere in this neighborhood, we'll have, I'll post the last, the final exam. Now, because the final period is from the 13th to the 19th, that means I don't have to have the grades ready till probably a few days after that, maybe even as far ahead as the following Monday. So you'll have plenty of time for that. Oh, is it May 3rd? I couldn't remember. All right, well, that's probably better. Let me go double check that. Oh, it's hard to imagine that we're already talking about May, for God's sakes.
It says no classes right there. May 3rd, no classes.
Well, yeah, it does say that. Oh my God, I never noticed that before. Okay, I knew there was going to be a Monday in May where we didn't have a class. Okay, so that would be the 3rd then. So probably, well, that means we have to wrap up everything on either the 6th or the 10th, because then after that, it's all officially final exam time. That's right. We'll figure it out. We got plenty of time. We're actually ahead of schedule. We definitely will not run out of time to wrap this up. So what that means is that there's plenty of time until the final exam. And again, it'll be online. You'll download it, take it home and do it at home and send it back. So it'll be low stress and that'll take care of that. And then after that, it's up to you to decide if you want to take more math classes. Well, we've got plenty of them if you're interested. We've got statistics, we've got pre-calculus. In fact, the statistics class is running during the summer in an entirely online format, if this stuff excites you, or you need an elective. I don't know how that works or what requirements they have, but I know that you have to have at least one math class to graduate. But there's nothing to stop you from having 2 or 3. You never know what might catch your eye when you look at that old schedule. All right. So anyway, yes. So as far as right now is concerned, just download the sample midterm number 2 from Moodle and have it ready by Monday. It's right there. I'm sure of it right now. There it is. And so that will be our Monday. When that's done, of course, we'll get back to chapter 11. All right. What else do we need to know? All right. Well, how about this? Now we're in the middle of chapter 11 and we still got a ways to go. But what I've done is I found a couple of videos which are only sort of indirectly related to what we're doing, but they're still interesting enough that I think it's worth our while to watch them. This refers to a very important figure in the history of mathematics named Pascal. You may have heard of this man before. Blaise Pascal lived in the 17th century in France, and he actually, not only was he a mathematician. Oh, you don't have yours? I thought I posted them all on.
I didn't get mine back either.
Isn't it there? Oh, I've spent so much time setting it up so you can see it on Moodle. And are you saying that it's not working?
No, I never saw it.
Yeah, I never got mine back either.
Oh, no, that's pretty annoying because I really spent so much time setting. I put it. Oh, for God's sake.
Yeah, I don't know.
Well, all right. Well, they're all in there. I don't know what.
Under what section?
Well, you know what? This worked for me the last time. I just created. There's something called Gradebook in there somewhere. Last semester,
Oh,
theoretically, we're supposed to get an email which said, "By the way, your grade is ready. Please go look at it." And then when you go into Moodle, there's supposed to be something called Gradebook, which shows the scores that you got.
oh,
Yeah,
I see it. I
checked
just got
mine's
an
there.
email, but now I looked in there and I got it.
Oh, it is there. All right, good. I'm relieved to hear that because I was very annoyed for a minute there. Now, there were 1 or 2 that aren't done only because I had technical issues, and those will be done very soon, but almost everybody has theirs right now. So if you're not sure, just go take a peek in Moodle. It should be there. Where exactly did you find it, by the way, Britt? Just in case someone else
If you
can't
go
find
to, okay. So you log into Moodle and you have the home page. And on the right side, the left side. On the left side, there's going to be something called categorized course list. You're going to hit spring 2021. You're going to go until you see mathematics for contemporary life. Then you're going to scroll down till you see it again. And then you're going to go to grades and it should say midterm 1 with your grade.
All right. So if anybody hasn't looked, I thought they were also sending out emails to let you know that something had been changed or you'd been. Otherwise, I would have sent out an email myself and said they're there. Okay. Well, now I know better. Next time when these are done, I'll send you an individual email separately and say, listen, it's ready. So, but at least you can see it. That's the important thing. And oh, yes. And by the way, yes, as we started to talk about, this is, yes, that Pascal of Pascal's triangle. But he's a very interesting figure in mathematical history. And also, when we're going to watch one video, which is a biography of Pascal, who had an extremely interesting background. And the second one is a brief discussion about Pascal's triangle, which you may have encountered before. It has so much useful information in it, but it does have some information in there which can be used to solve for the probability of a given combination taking place. So it does, on top of everything else, overlap with combinatorics, but it's an amazing thing to see. But in the meantime, why don't we just take a look at these 2 videos and then we can dive right back into chapter 11. All right, so first let me get that link going there. Here we go. So we'll start with the biography. And if you may have had some, you may have heard, about him, but I think you'll find this quite interesting. So there's the link. So let's check this out.
To his children and educated them himself and encouraged their intellectual pursuits. Blaise proved to be a child prodigy who developed a deep interest in mathematics and science as a young boy. Impressed by the boy's fascination with mathematical concepts, his father took him to meetings at the Mathematics Academy in Paris. At the age of 16, Blaise Pascal presented some of his early theorems, including his mystical hexagon, to the audience. In 1642, he started working on a mechanical calculator that could perform additions and subtractions after watching his father perform exhausting calculations and recalculations of taxes owed and paid. The device was called Pascal's calculator, or the Pascaline. He continued working on improving the Pascalines as there was a discrepancy between the calculator's design and the structure of the French currency of the time. He had made many improvements to the original design by 1645, yet the Pascalines were not commercially successful due to their high cost. During the 1640s, he learned of Evangelista Torricelli's experimentation with barometers. Following in his footsteps, Pascal experimented with how atmospheric pressure could be estimated in terms of weight. Through his own experimentation, he validated Torricelli's theory concerning the cause of barometrical variations and paved the way for further studies in hydrodynamics and hydrostatics. During the same time period, he invented the syringe and created the hydraulic press, an instrument based upon the principle that became known as Pascal's law. He made significant contributions to mathematics and published his Traité du triangle arithmétique, treatise on the arithmetical triangle, in 1653. The treatise described a convenient tabular presentation for binomial coefficients, now called Pascal's triangle. In 1654, he corresponded with the eminent mathematician Pierre de Fermat on the subject of gambling problems. The important groundwork laid by these two great mathematicians proved to be instrumental in Leibniz's formulation of the calculus. Pascal had an intense religious experience in 1654, after which he mostly gave up work in mathematics. Following this, he focused on writing on religious matters and published an 18-letter series between 1656 and 1657 under the pseudonym Louis de Montalt. In these letters, he attacked casuistry, a popular and ethical method used by Catholic thinkers in the early modern period, and this greatly angered King Louis XIV, who ordered that the work be shredded and burned in 1660. Blaise Pascal was of delicate health and suffered from several ailments during the later years of his life. He was working on an apology on Christianity, which he could not complete before his untimely death at the age of 39. The fragments of his work were later collected and published posthumously as the Pensies, which is today considered a masterpiece. In mathematics, his most significant contribution was the development of probability theory. He died in Paris, France on 19 August 1662 at the age of 39. Justice without force is powerless. Force without justice is tyrannical, said Blaise Pascal.
All right. Well, now you know who he is. Now let's see what this amazing triangle is all about. And you may have seen this before, or at least been exposed to some of it, but there's so much going on there. It's really an amazing thing that contains so much useful information, and mathematicians are constantly finding new applications of it. But let's take a look at this, and you'll see how fun and exciting Pascal's triangle really is. All right, so there you go.
This may look like a neatly arranged stack of numbers, but it's actually a mathematical treasure trove. Indian mathematicians called it the staircase of Mount Meru. In Iran, it's the Khayyam triangle, and in China, it's Yang-Wei's triangle. To much of the Western world, it's known as Pascal's triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs and you'll generate the next row. Now do that again and again. Keep going and you'll wind up with something like this. Though really, Pascal's triangle goes on infinitely. Now, each row corresponds to what's called the coefficients of a binomial expansion of the form x plus y raised to the n, where n is the number of the row, and we start counting from 0. So if you make n equal 2 and expand it, you get x squared plus 2xy plus y squared. The coefficients, or numbers in front of the variables, are the same as the numbers in that row of Pascal's triangle. You'll see the same thing with n equals 3, which expands to this. So the triangle is a quick and easy way to look up all of these coefficients. But there's much more. For example, add up the numbers in each row, and you'll get successive powers of 2. Or, in a given row, treat each number as part of a decimal expansion. In other words, row 2 is 1 times 1 plus 2 times 10 plus 1 times 100. You get 121, which is 11 squared. And take a look at what happens when you do the same thing to row 6. It adds up to 1,771,561, which is 11 to the 6th, and so on. There are also geometric applications. Look at the diagonals. The first two aren't very interesting. All ones, and then the positive integers, also known as natural numbers. But the numbers in the next diagonal are called the triangular numbers, because if you take that many dots, you can stack them into equilateral triangles. The next diagonal has the tetrahedral numbers, because similarly, you can stack that many spheres into tetrahedra. Or how about this? Shade in all of the odd numbers. It doesn't look like much when the triangle's small, but if you add thousands of rows, you get a fractal known as Sierpinski's triangle. This triangle isn't just a mathematical work of art, it's also quite useful, especially when it comes to probability and calculations in the domain of combinatorics. Say you want to have 5 children and would like to know the probability of having your dream family of 3 girls and 2 boys. In the binomial expansion, that corresponds to girl plus boy to the 5th power. So we look at the row 5, where the first number corresponds to 5 girls and the last corresponds to 5 boys. The third number is what we're looking for, 10 out of the sum of all the possibilities in the row. So 10 over 32, or 31.25%. Or if you're randomly picking a 5-player basketball team out of a group of 12 friends, how many possible groups of 5 are there? In combinatoric terms, this problem would be phrased as 12 choose 5, and could be calculated with this formula. Or you could just look at the 6th element of row 12 on the triangle and get your answer. The patterns in Pascal's triangle are a testament to the elegantly interwoven fabric of mathematics, and it's still revealing fresh secrets to this day. For example, mathematicians recently discovered a way to expand it to these kinds of polynomials. What might we find next? Well, that's up to you.
Okay, I guess we're all done. Well, that was interesting. Now, they're sort of throwing a hint at you towards the end there that maybe you should become a mathematician and study Pascal's triangle, because you never know what you might find in there. So you never know. You might decide 20 years from now, you might decide, you know what, I've had enough of this stuff that I'm doing now. I want to be a mathematician, and it could happen. All right. So let's get back to chapter 11. Now, we've been discussing quite a few topics in this chapter, and there's plenty more to come. So let me just quickly review what we've done up to this point. We started out by introducing combinatorics, where we learned about arrangements. Remember the 3-car garage case? We learned about permutations, where the objects are chosen in such a way that the order matters. We were introduced to the factorial operator. And then finally, we looked at combinations where the order of selection does not matter. And we saw formulas for all 3 cases based on the factorial operator. We learned how to do this on the calculators. And what else did we do here? Well, we started to look at probability theory, and we introduced the concept of the random experiment, which generates outcomes that we are studying. And we also introduced some key terms where we, for example, learned about the sample space, where we have a set that contains all the possible outcomes of an experiment. And then what we were just starting to do is look at how we calculate probabilities of these different outcomes. And so we had several good examples. We had the rolling of a pair of dice. Remember, there were 36 possible outcomes, all of which are listed here. So we can use this table to figure out the probability of any particular sum that we need from our dice. For example, if let's say you're playing a game and you need to roll exactly a 6 for whatever reason, let's say you need to land on Boardwalk in Monopoly, how many different ways can this happen? You can get a 2 and a 4, a 3 and a 3, and a 4 and a 2, as well as a 1 and a 5 and a 5 and a 1. So there's 6 of them, as we saw in this chart, 5 of them rather. And so the probability of getting a 6 on your next roll is 5 out of 36, which is approximately 13.9%. So knowing the different possible outcomes that can occur will enable us to calculate any probability of any sum that we need under any circumstances. And the idea here is that you're basically just counting them and dividing by the grand total, which is 36. All right, so we also looked at another simpler case where we roll a die twice, but this time we're only focused on whether the numbers are even and odd. Okay, so that way, instead of having 36 possible outcomes, we only have 4. And that really does make things a lot simpler. Now, we also did mention that in a case like this, each of these outcomes is equally likely, and we proved it. For example, if you're interested in knowing the probability of getting 2 consecutive even numbers, all you have to do is look at this chart and count all the different ways in which you can get 2 consecutive even numbers. For example, 2 followed by 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, and then finally 6, 2, 6, 4, and 6, 6. So altogether, that adds up to 9 possible ways of getting evens on 2 consecutive rolls. And so therefore, the probability of that happening is 9 out of 36, which is 1/4. So each of these falls into that same category. If you wanted to prove it, you could go back there and look at that chart, and you'll note that, for example, even followed by odd. How many ways can that happen? Well, let's see. 2, 1, 2, 3, 2, 5, 4, 1, 4, 3, 4, 5, et cetera, and you'd see that once again, there's 9 ways this can happen out of 36, which implies a probability of 1/4. So this makes things very simple for us because we now have all the different possible outcomes of this experiment are equally likely, and we can gather these up into a special set, which is called a sample space, and we can use that sample space to calculate any probabilities that we might need. All right, so in this case, and by the way, of course, I've reduced the word even to E and the word odd to O just to save writing time. So here's our sample space for this experiment of rolling the die twice, where we only are paying attention to whether the number is even or odd. So instead of having 36 outcomes, we have 4, all of which have a probability of 1/4. With that information in mind, we can calculate other probabilities very simply and easily. So, for example, what kinds of probabilities might we be interested in? Well, before we answer that question, we went ahead and reviewed set theory, just in case it's been too long since you've seen this stuff before. We introduced the concept of the union, where we combine 2 sets. We introduced the concept of the intersection, where you look at a new set that's created by looking at what's common between 2 existing sets. And we also introduced the concept of the subset. So you might recall that a subset is a set that is completely contained within a larger set. So in this case here, where you're looking at A, B, C, and D, you can see, oh, look at the wrong one, sorry, subset. D is a subset of A because all the elements in D are also elements of A. Whereas here we can see that C is not a subset of D because the elements in C do not belong to D. All right, so therefore C is not a subset, and we use this symbol, subset with a slash through it, to indicate that C does not or is not a subset of D. All right, so what we're doing now is formally defining a very important idea in probability theory called the event. An event is a special kind of set. It is created by taking a subset of the entire sample space. And now, of course, we define what an event is. We have to be careful about the way we define events. We have to make sure that whatever we choose is in fact a subset of the original sample space. So here, when we roll the die twice, we can define the event F to be at most one even number turns up, which is the same thing as saying we either have one even number or none. Which means that if you look at all the different possible outcomes up here on the top in the sample space, all of those actually qualify except for EE. We do not choose EE for this set because there we have two even numbers and we're restricting ourselves to one or none. So you can see all the elements in F are clearly elements in S, and therefore F is a subset of S, which we write with this symbol. It looks like a little c, but this is actually the subset symbol. And that being the case, F qualifies as an event. That's all it takes. F only has to be a subset of S in order to be qualified as an event. The question then, though, becomes how do we calculate the probability of F? That's the question. How do we know what that probability is? Well, in general, there's a couple of ways we could go about this. In the specific case, well, actually, let's jump ahead here and look at this slide. What I want you to notice here is that F is a set that contains three possible outcomes. What we can do in general to calculate this probability is break it up into the sum of the probabilities of each individual element of set F. Okay, in other words, the probability of F is the same thing, and this is, by the way, based on the axioms of probability, because all three of these events are mutually exclusive of each other. So this is just an application of the third axiom of probability. So there we go. You can see that F itself is a set that contains EO, OE, and OO. So the probability of F could be calculated as simply the probability of EO plus the probability of OE and the probability of OO. And again, this is due to the third axiom of probability. Now, we've already seen that each of these elements of the sample space has a probability of 1/4. So when you add up 1/4 plus a fourth plus a fourth, of course, you'll end up with 3/4 or 0.75. So this approach that I've just showed you will work for every situation, whether the elements in the sample space are equally likely or not. So this approach is always available to us. Now, it turns out, though, that in the special case where all the elements in the sample space are equally likely, there's a quicker way of doing this. But remember, it only works when all the elements in the sample space are equally likely to occur, as they are up here. These are all equally likely. So when that happens, here's what we do. No matter what event we're looking at, its probability equals the number of elements in that event divided by the number of elements in the entire sample space. So for F, look how easy this would be. F has 3 elements in it, S has 4 elements. Therefore, this ratio would simply be 3 out of 4. All right, so that little n, this simply means number of elements in that set. So therefore, going back to our example, you can see that given that F has 3 elements in it, S has 4, that ratio is 3/4 or 0.75, which is exactly what we received previously when we calculated each one separately and added them up. But remember, this only works when all the elements in S are equally likely. It's a shortcut. It's helpful, but remember, we can't always use it. Now, because this might be interesting, suppose that we changed our random experiment slightly. We still have the dice. We're still only focused on evens and odds, And instead of rolling the die twice, we decide to roll it 3 times. How would that change our results? Well, for sure, the sample space would be bigger. There are more possible outcomes now when we roll the die 3 times than twice. The question is, how many more? Okay, well, let's find out. So if we roll the die 3 times instead of 2, with the same understanding that we're only focused on evens or odds, what is the new sample space? What elements are in that new sample space? All right, so as a rule of thumb, every time we roll the die again, but when we're focused on evens and odds, we're doubling the number of outcomes. Doubling every time. So therefore, it stands to reason that when we roll the die 3 times, the number of outcomes doubles from 4 to 8. And that's exactly what happens. All right, and now what we want to do is figure out what are those new outcomes. All right, so I wrote them down here, and you can see, wow, this is getting pretty long. Look at all those possibilities. So you've got 3 evens. There are 3 different ways of getting 2 evens. Okay, the odd number can come first, second, or third. There are 3 ways of getting 1 even, where you can see that the even number comes first, second, or third. And then there's only 1 way of getting no evens, which implies all odds. So suppose that A is the event of getting at least 2 evens when we roll the die 3 times. What is the probability of this happening? Well, what elements in this sample space qualify as having at least 2 even numbers? All this really means is that you have either 2 evens or 3. So if you go here, you can see, oh, look, what a lucky coincidence. All of them are listed right here on this top row. These are the cases with 2 evens, and this is the case with 3 evens. Altogether, there are 4 ways this can happen out of 8 possibilities, all of which are equally likely. So I can calculate each of these separately and add them up, but there's no need because the entire sample space consists only of equally likely outcomes. So instead, I'll just note that there are 4 elements that belong to A out of 8 in the sample space. So that ratio is 4/8 or 1/2. And that's it. That's all I had to do. The probability of getting at least 2 evens is 1/2. Nice. So it's pretty straightforward. Now, as I said, every time now, because we're only looking at 2 possible outcomes in each roll, every time I roll the die, I'm doubling the number of possible outcomes. So I put together a small chart here so you can see how quickly this grows. All right, so for example, if the number rolls is, let's say, 1, well, then only 2 things can happen, even or odd. With 2, we've already seen 4 of them can happen. With 3, we've now just seen that there are 8 possible outcomes. But as you keep going and rolling the die more and more times, with 4, for example, there are 16 outcomes. And then finally with 5, there are 32 possible outcomes. And it just keeps going on and on and on. So you've got with 6, you would have, for example, 64 possible outcomes. Now, we're not going to have any like that on the test or on the practice problems, but you should be aware that this is how it works. All right, now, just as a side note, remember, up to this point, we've been calculating the probabilities of events when the sample elements are all equally likely to occur. And again, let's go back and revisit the case where we were rolling the die twice, But this time we were actually looking at every single outcome. So in other words, we had 36 possibilities. And what we'd like to be able to do is calculate probabilities based on this case. And let's say that our focus is not on the actual numbers themselves, but their sums. How would that work? How would we calculate probabilities in this case? All right, so let's go back and remind ourselves. Well, first of all, in that case, the sample space would be the numbers 2 through 12. But unlike the case with the E's and the O's, these outcomes are not all equally likely. Okay, not. In other words, the probability of getting a 2 is very different than the probability of getting a 7. All right, so I've put together, and I've copied the chart again that we put together earlier that tells us what all these probabilities actually are. Okay, and so we've already seen how they were derived. For example, if I want to know the probability of getting a 7, what do I actually have to do? Let's go back to my chart and count all the ways in which I can get a 7. All right, that would be 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and finally 6 and 1. Those all give us a sum of 7. How many ways can this happen? Altogether, we count 6. 1, 2, 3, 4, 5, 6. There's 6 ways of getting a 7 out of 36 possibilities, each of which is equally likely to occur. So that implies that the probability of 7 is, hold on, I lost my place. Oh, here it is, 7, is 6 out of 36, 1/6 or 0.167 or 16.7%. So the probabilities in this sample space are very different from each other, aren't they? So what if I wanted to know something like this? Suppose I have an event that represents getting at least a 9 when we roll the dice. Well, in that case, then there's nothing you can do except literally add them all up. In other words, we need the probability of getting a 9 plus a 10 plus an 11 plus the 12, which you can take off that chart, and you can see that they are 436, 336, 236, 136, and that all adds up to 1036, as you can see.
Can you put back up the sample space for a second? I didn't finish
Yes.
copying that.
Yes,
Thank you.
right there.
Okay.
All right, good. All right, so anyway, but you can see here we can calculate any probability that we choose, but with the understanding that you must now calculate these individual probabilities separately and then add them up. In other words, you're not going to take 4 here. You're not going to add up and come up with like 4 out of 36, for example. Instead, each one of these has a different probability, which we must combine to come up with our final result. Okay. Now, here's another example. What if we are using a pair of non-standard dice? Not all dice are the same, by the way. I think I showed you this picture last time. You figure, well, all dice are the same, but there do exist dice for specialized games. Yes, that's right. Exactly. Now, I've never played Dungeons and Dragons, but I know that there are many different kinds of dice besides the standard ones. And you can see some of them. Like here, these have 12 sides. Oh, see, I don't know that. I mean, I know of it, but I don't ever know. I've never played that game. In fact, I don't think I've ever met anybody who's ever. Oh, is this the game this is the one they use? The 12-sided die?
Well, there's all kinds of dice, right? So there's D6, so you can roll to like add power to your weapon. There's a D20, which you can roll when you're attacking an enemy, or if you want to do something, your dungeon master might say like roll your D20, which is the same thing as a D12, but with more sides.
Ah, okay. All right. Well, now we know. And you can literally buy them that go all the way up as high as 100. I don't think it goes beyond that. So the possibilities are endless when you come right down to it. Polyhedral. Let's see, how many of those? Geez, look at these guys. There's some wacky ones. Look down here. But yeah, so I'm trying to imagine a game that needs. This one seems to only have 4 sides. Oh my God. Jeez. They're actually kind of cool. Or in fact, they're kind of works of art. Wouldn't you agree? This one has 20. These have 8. That must be quite an engineering challenge to make dice that have all these weird numbers of sides. Oh my God. That is wild.
You know what's truly wild? Trying to stack them. Like when it's not
Oh.
your turn, you're playing with a lot of players, and you try to stack all the dice. Can't do it.
I can imagine that because they're getting a little clunky here. I don't
Yeah.
imagine they stack up very well. I mean, look at these things. Look at that. That's a 50. Oh no, it's got a 70. Oh my God. There you go, our old friend. But that one's black, which is kind of unusual. But man, the possibilities are endless. Endless, I say. Yeah. But of course, traditional games like our beloved Monopoly always only had the 2 normal die, 1 through 6, 2 dice. That's how the game works. Okay, that's how it was created. Actually, the game of Monopoly itself has a very interesting history. It was invented during the Depression, and apparently, you know that originally, I mean, it was made by Parker Brothers, which eventually was bought out by Hasbro, I think, or Milton, one or the other. Well, anyway, so what happened was the guy who invented the game brought it to Parker Brothers, and at first they thought, I don't know, maybe we kind of like it, we kind of don't. They basically told him to take it back and work on it some more. So he originally, and this is in the 20s now, he originally went there asking for $500 for the rights to publish this game. And when they said, no, take it away, we need you to do some more work on it. And he did, and he brought back the version that we now know and love. But this time he got clever and he said, listen, you can have this game, the rights to the game, but it'll cost you $500. And then also I expect you to give me a share of the royalties. And that was a big deal because they've sold tons and tons of games ever since then. And so because of that, his heirs are independently wealthy because of those royalties. If he hadn't gotten those royalties, he would have gotten $500 and that would have been the end of it. The guy's, his name was Charles Dow, I believe. It was Dow. I forgot, maybe his first name wasn't Charles, but he invented this game and, well, it really caught on, as we know. But it was kind of an interesting, I mean, in those days, board games weren't as well known as they are now. And so all of the properties in Monopoly, or at least the American version, are based on Atlantic City, which at the time was, of course, one of the major resorts on the East Coast. Now it's more of like a gambling town. But so the game itself is very interesting. It has a lot of interesting features to it and historical information in it. And so it's actually quite an interesting game, and its history is very, very, very interesting. But anyway, let's get back to this. So in this example that's coming up next, we have dice. If they even exist, I don't know, where there's 6 sides, but only 2 even numbers and 4 odd numbers. That's kind of weird. And then we roll the die twice like we did before, but now the probability of getting 2 even numbers is going to be very different than what it was before. Because the probability of getting an even is not 1/2 any longer. Instead, it's only 1/3 because only 2 out of the 6 sides are even, which means that odd has a probability of 2/3. And so these are the individual probabilities, which you see are no longer 1/4. EE has now a probability of 1/3 times 1/3, or 1/9, because there's an even followed by an even, each of which has a probability of 1/3. EO therefore must have a probability of 1/3 times 2/3, or 2/9. OE is now 2/3 times 1/3, or 2/9. And then finally, OO is 2/3 times 2/3, or 4/9. So then the probability, therefore, of getting two even numbers, I'll just add this separately, and that's 1/9, okay, instead of 1/4, because of the way the dice is structured. So our sample space hasn't changed, but the probabilities are now very different. So I'll add that here. Note that the sample space hasn't changed, but the probabilities are no longer of the individual events or elements are no longer equal to each other. So now here's what we're going to do. Let's go back and revisit that event F that we had earlier, which recall F is the event that we get at least one or at most one even number. Previously, the probability was 3/4, but look at it now. At most one even means EO, OE, or OO, and so now we have to add them up separately. We can't just do 3 out of 4 any longer. And when we add them up, you end up with 8 out of 9. So the fact that the die itself is now different changes everything. Even with the same event, even with the same sample space, the probabilities are different because they're not all equally likely to occur. Okay, now all of that related to calculating the probability of a single event. What if instead we have a situation where we need to calculate the probability that some combination of events is taking place? In other words, more difficult or more complex situations are taking place, and it will happen. And so in order to calculate these probabilities, 3 rules were invented during the centuries to help us deal with these types of probabilities. So I'm going to show you the list. The first 2 are relatively straightforward, and we'll do them today. The last one is very complicated, and therefore it will have to wait till Monday. So, but we have plenty of time to cover the first 2, and you can see their names are. First, we have something called the addition rule. Secondly, we have something called the complement rule. And then finally, we have the one that we have to save for Monday, the multiplication rule. Okay, so what are these all about? Well, the addition rule is actually just a rule for calculating the probabilities of unions of events. Okay, so, and by the way, now it'll really help us that we reviewed set theory last time, because if you forgot what union means, that would have made things just a little bit awkward. All right. So let's see what this is all about. For any 2 events A and B, the probability of their union, which can also be expressed as or in English, equals the probability of A plus the probability of B. But you notice there's a wrinkle here. At the end, we have to subtract this thing, which is the probability of A intersect B which is also known as the probability of A and B. Then with all of that, we'll have our final result. The probability of A union B will come from this rule. So conceptually, it's not all that complicated, but we do need, in order to do this, to come up with the probabilities of A and B and the intersection before we do this. By the way, before we're done, we're going to explain why that last piece is needed. Why, I mean, you might think we would just add these two together, but that's not the way it works. We do have to subtract this intersection, and you'll see why in a few minutes. All right. So let's look at some examples. Let's go back and revisit the case. Now we're going to going forward here. We're going to assume that we're back to our original example. We have the sample space with 4 elements, each of which will be assumed to be equally likely. In other words, we're rolling the die twice, and they're normal. It's a normal die that we're rolling. So therefore, all of these outcomes are equally likely. So if you recall, the sample space is equal to the set containing EE, EO, OE, and OO, where each is equally likely. Now, A will be defined as the event that the first roll is even. And you can see that out of all 4 of these, this is only true in the first 2 cases, EE, EO. B will be the event that exactly one roll is odd, which means OE and OO, OE and EO. Now, by the way, both of these qualify as events because, as you can clearly see, they're both subsets of the sample space, and therefore we can calculate their probabilities. All right, in fact, you can already tell that the probability of A must be 2/4 or a half, and the same thing is true with the probability of B. Okay, now let's do the calculations. What's the probability that either the first roll is odd, or exactly one roll is odd, or possibly both? So the question is, what's the probability of the union of A and B? Meaning that we're getting either an even roll on the first roll, or we get exactly one roll that's odd, or possibly both. Now, what we need is 3 probabilities to do this. We need the probabilities of A, B, and A intersect B to fill into this formula. Okay, so we need these, this has to come first. We need to calculate these 3 probabilities and then add them, or combine them in the way that you see here with this formula. So let's go take a look. Now remember, we're still dealing with a case where we have all equally likely outcomes. So here, for example, the probability of A is easy to obtain. It's simply 2 out of 4 because the sample space has 4 elements. B is the same, it's just 2 out of 4. Now here's an interesting one. The intersection between the two contains just 1 element, EO. They both contain an EO, therefore their intersection is the element EO, which itself must have a probability of 1/4 because there's only 1 element in the set and the entire sample space has 4. So we're basically all set. Now it's just a question of plugging in these numbers into the addition rule and coming up with our result. And let's take a look. Here we go. If we plug in all those numbers, we get 1/2 plus 1/2 minus 1/4, which equals 3/4. That's our final probability. All right. Now we can confirm this very quickly and easily by actually writing down the elements that belong to this union. The alternative that was open to us was to not use this rule, but because these sets are relatively small, there's nothing to stop us from taking advantage of the fact that the outcomes are equally likely. So what we can do here is just note that with A being EE and EO, and B being OE and EO rather, their union looks like this. You've got these three elements in common, between the two rather. And as we've said before, even though they both have an EO, we do not need to list that twice. We think of this as having three elements in it. And since all the elements are equally likely to occur, that means that this probability of A union B equals the number of elements in A union B divided by the number of elements in the sample space, which is 3/4. And that would have done the job too. As it turns out though, in many cases, if the sample size is large, or at least not tiny like it is here, often the best way to do this is to use the rule rather than trying to count, because then the counting can get very awkward very quickly. So it's nice to know that either of these options can be used, but usually for fairly sophisticated situations, the addition rule is probably the easiest thing to do. This counting thing that we're doing works well only when the sample space is very small. All right, now with all that being said, I did mention earlier, we would like to understand how come the rule is set up the way it is. In other words, why is this last intersection here? What's going on with that? So on the next slide, I've produced what's called a Venn diagram, which will help us understand why the rule works the way it does. It's often, you know, the thing is with rules is you can certainly memorize them and certainly apply them, but ultimately it's certainly helpful if you understand how they work and where they came from in the first place. It's, you know, the thing is, it's easy, you can try to memorize something and then you can forget it. But once you understand something, you realistically can't ununderstand it, so to speak. You can forget knowledge, but you can't forget understanding. So what's happening here is this. Using the same example, let's draw that Venn diagram. So here set A contains EE and EO, and set B contains EO and OE. And we note that where they intersect, we have the element EO. So when I add them together to come up with that union, if I just do A plus B, and by the way, these Roman numerals represent regions. A is the region where we have just the elements that are in A only. 3 is the region where we have the elements in B only. And 2 is the region where they overlap. So A would therefore consist of regions 1 and 2. B is 2 and 3. If I try to add these together without subtracting this intersection, I'll end up with 1 plus 2 plus 2 plus 3, and I will therefore count this intersection twice. Therefore, to compensate for that problem, I subtract the intersection, which is 2, and look what happens. The union has a probability equal to region 1 plus region 2 plus region 3, and we're all set. So that's why we need to do this, because otherwise we'll count the intersection twice. We don't want that, obviously. And by the way, OO is down here because it's not part of either set. So that, I hope, in a nutshell, will help explain why we need this intersection here, the subtraction, when we use our rule. Now, it turns out, though, that when we have a union like this, it is not necessarily true that A and B intersect each other. They did here, but it doesn't always work that way. So it turns out there's a special version of this rule, which is applied to cases where A and B do not overlap. In other words, A and B are mutually exclusive. So the specialized addition rule, or the simplified version, only applies when A and B are mutually exclusive. And the reason why we can do this is because mutually exclusive means that A intersect B is empty, which implies that the probability is 0 because this is an impossible event. Okay. So what would that look like with a Venn diagram? Well, it means that we would have two sets that have no elements in common. And so therefore, unlike the previous diagram, there's nothing where there's no place where they intersect. Let's put it that way. All right, so let's see what this is all about. So you've got two sets, and whatever's in them, we don't need specific examples here. You can see that they do not overlap or intersect. Their intersection is there for the empty set, which implies that the probability is 0 of that intersection. But this, remember, only works when A and B are mutually exclusive. Okay. Well, what is the implication of this? Well, it means that if you look at this rule, since that probability is 0, we can just drop out that last term, and what's left is the so-called simplified addition rule. So we leave out the intersection because it has a probability of 0. And that's it. So from now on, this will be known as the simplified addition rule. All right, so let's look at a quick example of this. Suppose that we have the same experiment. We roll the die twice. Each outcome is equally likely. But now this time A represents the event that the first roll is even, and B is the event that the first roll is odd. Now clearly you can see these do not have any elements in common. They are mutually exclusive. Okay, now let's apply the rule. We want to know the probability of A or B. In other words, of getting either an even or an odd on the first roll. So as usual, we'll figure out the probabilities of the individual elements of that formula, which means we need the probability of A and B, each of which is a half. And so of course, just as a quick reminder, this is empty, therefore this probability is 0. Because A and B have no elements in common. So therefore, the probability of getting A or B, we can use the our simplified addition rule, and therefore we just add up the two 1/2 and we end up with 1. That's because, and that's only though because we know for a fact that A and B are mutually exclusive. If we don't know that, we can't really use this rule. Now, just like before, with the full version of the rule, we can actually do this in a slightly different way. Instead, what we could have done is taken our union and figured out what elements belong to it, and then count them. All right, so how would that have worked? Like here, you notice how I've got A and B listed there. The union is where I just combine them, and you can see that their union is those 4 elements, and therefore, because they're all equally likely, that probability is 4 out of 4, which is just 1. Or in this specific case, you can see that this union is in fact the sample space, and we know that it must have a probability of 1. All right. Now, with all that being said, we're going to do this complement rule next. The complement rule is very basic and straightforward, but first we have to explain what the word complement means in this context. Okay, otherwise none of it will make sense. All right, so what exactly are complements? So I just want to point out that the word complement can have many different meanings in English. You've probably encountered several of them already. Now, by the way, don't confuse it with there's another word, complement, which is spelled differently. The one that means you say nice things to people, that is spelled differently. That is not the same thing. Here we're looking at the word complement spelled with an E. And what am I talking about? Well, let's find out. The word complement spelled this way can have many meanings. In economics, if you've ever had any economics courses, you might recall that in economics, 2 goods are said to be complements if they're consumed together. For example, ketchup and French fries, spaghetti and meatballs, you name it. Any goods that are consumed together are referred to as complements. In geometry, you might recall that angles that add up to 90 degrees are also said to be complements. Here, though, it has a different meaning altogether, but yet it also refers to the idea that these are events that have some connection with each other. They somehow go together. So we'll start out by formally introducing their definition, and then we'll look at some examples. Because otherwise, the definitions are important, but I don't think you'll get the point unless you see some actual examples. So what does it mean for 2 events to be complements? Well, 2 things must be true. First, their union must be the entire sample space. And second, their intersection must be empty, which means that they are mutually exclusive. If both of these things are true, then A and B are complements. If one or the other is false or both, then they are not complements, and we may not use the rule. All right, so that's what it takes for 2 events to be complements. The union is the entire sample space, but their intersection is empty. All right, so I've come up with some examples that I think will make a lot of sense to you. For example, how about these? Suppose that we're looking at the cards in the deck. We have a deck of cards, and we are drawing a card out of that deck. Our experiment, in other words, consists of picking a card from a deck, which means that the sample space is the deck. And then we're going to define 2 sets. The first set would be the reds, and the second set would be the black cards. So we can demonstrate that the red and the black cards are considered to be complements because of 2 reasons. Number 1, all the cards in the deck are either red or black, which in parentheses, I've noted that this is the equivalent of saying the union of the set of red cards and the black cards is the entire deck, which is our sample space. So there aren't any, for example, green cards in there. It's all red or black. So that condition has been met. Okay, but there's more. There's one other condition that has to hold in order for them to be considered complements. And that condition is that A and B must be mutually exclusive. Well, are they? Yes, absolutely, because there can't be any cards that are both red and black. So guess what? Red and black cards are mutually exclusive sets. And so we've satisfied both requirements. Therefore, red cards and black cards are complements of each other. All right, red and black cards are complements. So based on the same logic, we can say the same thing, for example, about, how about the black and white pieces on a chessboard? Their union is the entire set of pieces, but they are mutually exclusive. And then here's another one. How about the odd and even numbers in the set of all natural numbers? All the natural numbers are either odd or even, and none of them can be both. So therefore, that's another set of complements. Now, here's an example where we have two sets that are not complements. And I want you to see why. All right. How about if I don't look at the red and the black cards, but instead I only look at the diamonds and the hearts? Okay, so we're going to prove that those are not complements. They only satisfy one of the two required conditions. First, they are mutually exclusive, which is important, but here's the problem. Their union is not the entire deck of cards. In other words, this union that we create from the diamonds and the hearts is leaving out all the spades and all the clubs. In other words, the black cards are missing. So therefore, the set of diamonds and the set of hearts are not complements of each other. And it's because their union is not the entire sample space or the deck. All right, now we're going to introduce some new notation here. It's very simple. If you have an event A, its complement is written as A with a little c, superscript. AC represents a complement. So whenever you see that from now on, that means a complement. So the rule that ties them together is very easy. It can be expressed in two different ways. So let's see them. All right, the probability of A complement equals 1 minus the probability of A, and algebraically, this is equivalent to saying that the probability of A equals 1 minus the probability of A complement. That, in a nutshell, is the complement rule, and you can see it's easy. The question is why? Why is this true? That's what we'd like to ask ourselves. Why is this true? And it turns out this has something to do with the addition rule. And in fact, you can think of it as almost as like an extension of the addition rule. So what do we mean by that? All right, well, let's go back and revisit our examples with the two die, or the die being rolled twice, where they're all outcomes are equally likely. And so let's say that we define the following events. In event A, the second roll is even, and in event B, the second roll is odd. So here's the big question. Are these complements? Why or why not? Ooh, now remember, there's two things that have to be true for them to be complements. One of them is that they're mutually exclusive, and you can see that they are because they have no elements in common. The other thing that needs to be satisfied is that their union must be the entire sample space. And if you look at them very carefully, you'll see that all the elements in those two sets represent the entire sample space. So what that means is that events A and B are complements. The fact that we got an even number on the second roll and the fact that we got an odd roll, those represent complements. Well, that means that we can use the complement rule to calculate probabilities about these two events. Yeah, so for example, A is EE and EO, or OE, which means that its probability is a half. And B, same thing. Their union is the entire sample space. Their intersection is empty. By the way, so what we're going to do now is change the notation a little bit. Because they're complements, we're going to replace B with A complement. Okay, because they are complements. And so when we go to the next slide, we'll see how to calculate their probabilities from each other. All right. So here we go. So again, because of the way A and B are defined, and because we know that they're complements, the probability of A is 1/4 or 2 out of 4. 2/4 or 1/2. B or A complement is 2 out of 4 or 1/2. And you can see that both versions of the rule do work out. And of course, that's because we know that these two events are complements. All right, now we're almost done here. I just would like you to see how and why this rule is derived. What's going on with this? Oh, sorry, there's one more example. Then we'll look at why this rule works. Okay, very good. So imagine the following situation now. A is a card chosen. A card is chosen from a deck. That's our experiment. S is the entire deck. Let's let A represent the card is a royal card, and then B represents the fact that B is not a royal card. So what is the probability of A? Now, are A and B complements? Oh, I forgot to ask that question here, didn't I? All right, so let's go back here. So how do you know? Now, by the way, if you're not familiar with cards, the royal cards are the Jack, Queen, and King in each suit, and the rest are not royal cards. Ace, 2, 3, 4, all the way up to 10 are not considered to be royal cards. So the bottom line is that A union B, the union of A and B, is the entire deck, but A and B are mutually exclusive. Therefore, A and B are complements. Okay, now, that being the case, if I want to know the probability of 1, I can use it or obtain it from the complement rule. Now, if you count, now remember here, we're also assuming that all the elements of the sample space are equally likely. Each card has a 1 out of 52 chance of being chosen. So that being the case, the probability of A, the royal cards that is 12 out of 52. The probability of B would therefore be 40 out of 52. And you can see that these two are tied together by the complement rule. In other words, if I didn't even know what the probability of A is, it doesn't matter because I can obtain it as 1 minus the probability of B, which also works out to be 12 out of 52. All right, so all that remains is the proof as to why this rule works. All right, so this will only take a minute. Okay, how is the rule derived? Let's find out. Now, we already know what it means to be complements. All right, so I wrote that down one more time. We know that for A and B to be complements, either it must be true that both the intersection is empty and their union is the entire sample space. So what I'm going to do is apply the traditional or the false addition rule to these two events, A and B, assuming that they are in fact complements. Okay, so in other words, if A and B are complements, what I want to do is calculate the probability of their union with the traditional or full addition rule. But you'll see that we can make some changes to it. Now, first of all, this is the full addition rule. I can set this last intersection equal to 0 because we already know that A and B are mutually exclusive. So that leaves us with the simplified addition rule down here. But we also know one other key detail that will help us simplify this even further. That other detail is that A and B have a union that equals the entire sample space. So I'll add this at the top, just a little helpful hint. Recall that from the rules of the axioms of probability, the entire sample space has a probability of 1. And since A union B is the entire sample space, then this term in the beginning must be 1. All right, so therefore, look what happens. If that union equals 1, look what happens to our situation. 1 equals the probability of A plus B, which gives us right here the two versions of the complement rule. And that's it, except that with the rule, we replace the B's with a complement, but it means the same thing. So in other words, the reason why this is working is because we have the knowledge that A union B is the sample space. They are mutually exclusive. So when we throw them into the addition rule, this is what results. Okay, so like I said, the next section of this chapter is the multiplication rule, which is pretty complicated, which needs a little bit more background before we can dive right into it. So we'll obviously hold that off until Monday. And then in the meantime, don't forget about this sample midterm. We're going to go over it on Monday, and then I can post the actual test, which will give you a week to do it. Okay. And remember, keep in mind, this one won't take quite as long as the first one because it's only based on one chapter, which is kind of nice. All right. In fact, usually most people find in this class that the first midterm is the hardest test of all 3 of them. So if you did well in the first midterm, you should be aces for the rest of the semester. Okay. So, all right. So if there's no last minute questions, I guess we can stop right here. And I'll see you all on Monday.
Bye. Thank you.
Thank you. Have a
Okay.
good weekend.
All right. Bye.
Thank you.
Okay. Bye.